The module design loads calculates the most critical characteristics of central air conditioning systems, heating, cooling, and ventilation air requirements for commercial and institutional buildings. Many software tools calculate heating and cooling loads of buildings. However, all existing tools are not compatible with other tools, sizing piping, ducts, and other elements of HVAC systems that use the heating and cooling loads as input data. In the course of design, the architect or building owner often changes space layout and occupancy of the building. As a result, the mechanical engineer performs iterations of the entire chain of calculations that support the HVAC system design. The iterative manual transfer of computation results from one tool to another becomes a source of frustration, wasted time, costly errors, and excessive project development costs. In order to avoid the shortcomings of existing tools, we have developed a suite of coded spreadsheets. We call them modules, all based on the same MS Excel platform. The modular format of the spreadsheets will allow you to link them into a customized computational system. The system will automate the calculations, and thereby significantly reduce design time and human errors. The Design Loads module is compliant with latest methods and standards of American Society of Heating, Refrigeration, and Air Conditioning Engineers. The system range that can be simulated by the module includes any combination of constant and variable air volume air handling and makeup air units, with terminal reheat coils, and perimeter heating units. The module exposes virtually all calculation lines, allowing for visual control of the intricate load calculation sequences, and studying of the simulated load sensitivity to various inputs. These features are beneficial for both real HVAC system design and training purposes. This tutorial will demonstrate you how to use the module design loads for design of the sample building, as described in the Tutorial 1, Introduction. The module consists of worksheets with yellow tabs, populating all input data, a red tab worksheet, with a set of calculation reports, and a number of worksheets with gray tabs, summarizing intermediate calculations. Let us overview the data input process for the sample building, as described in the Tutorial 1, Introduction. The worksheet climate requires to input building location, odesic coordinates of building, design ambient temperatures and humidity, and other climate conditions of the geographic region. In the building input worksheet, enter number of occupants, building floor area, elevations orientation, and lighting type. The worksheet envelope inputs is the interface for entering envelope-related data. In this and further worksheets, white cells require manual input of data, and gray cells return calculated interim or final results. We have learned from the sample building wall schedule, described in the previous tutorial, that the wall consists of the following layers. 4 inches of brick, 1 inch of airspace, fiberboard sheathing of 1/2 inch thickness, 3.5 inches of bad insulation, and 5/8 inches of gypsum board. As we entered the layers material and thickness, the code has calculated thermal resistance of the layers and wall in total. The other inputs relate to arrangement of roof, window, external shades, entrance doors, and basement. The tab space input allows you to specify space-related information. Let us consider assembling room inputs. This room has 44 feet long north wall, 39 feet east wall, and 11 feet south wall. Let us enter the information gathered from the sample building drawings. 44 feet for north wall, 39 feet for east wall, 11 feet for south wall, 1,580 square feet floor area, slab on grade floor type. 1,700 square feet roof area. 3 north windows and 4 east windows. Based on selected occupancy type, the code will determine the space occupancy density, the maximum number of people in the space, and lighting power input density, as recommended by Ventilation and Energy Standards of American Society of Heating, Refrigeration, and Air Conditioning Engineers. Column AM is designated for input of occupant activity level. For the assembling room, the closest activity level is moderate active office work. The selection determines the percent of radiant heat from the occupants, and the sensible and latent heat gain rates per person automatically appeared in the nearby columns. The code will use all these space inputs to calculate the heat gain rates from occupants, lighting, equipment and envelope, and will simulate space-related cooling and heating loads. The worksheet system inputs allows you to configure general concept and controls of up to 3 regions in the building. In the tutorial introduction, we determined that the design concept of the system to serve the occupied spaces in sample building is a constant air volume single duct air handling unit with terminal reheat coils, perimeter heating units, and ducted air return. In accordance with the concept, let us select the system S1 as an air handling unit with constant supply airflow control, reheat coils, perimeter heating units, and ducted air return. The system serving boiler and other unoccupied rooms includes only local space heating units. Accordingly, the system S2 will have the following inputs. The next worksheet requires design indoor air temperature and humidity ratio values for each system in the building. The tab zoning allows you to group building spaces into individual comfort zones. Each zone represents a reheat coil or motorized damper controlled by a thermostat. For example, we will assign assembling room to be served by an individual terminal unit, called Zone 4, that belongs to System 1. We will assign the small rooms, washdown room, dark room, screen room, and the office, to be served by one terminal unit, called Zone 5. Notice that column D automatically detects any human errors during the zoning procedure. The other worksheets with yellow tabs summarize interim simulation results based on the provided inputs. The worksheet titles include space ventilation, fans, cooling coils, heating coils, reheat coils, space heating units, and boiler plant. The worksheet reports populates the interim results in printable set of reports. The first 4 reports provide the input summary used in computations. Report 5 provides the outdoor, exhaust, and supply air volume rates for each room. Report 6 outlines the heat loss breakdown and total design heat loss rate per space. Report 7 provides you with the cooling load breakdown and design cooling load rate for each space in building. Report 9 summarizes the total design space-related sensible and latent cooling load rates, supply airflow rate, and outdoor airflow rate for each system in the building. Reports 10 and 11 will provide you with design operating conditions of the supply and return air fan S in the building. For each air system in building, Report 12 provides the full air balance, design summer psychrometric, cooling load, and the air supply density benchmark. The heating coil design characteristics can be found in Report 13. Report 15 outlines the building heating balance and heating load density benchmark at design winter conditions. Reports 17 and 18 populate the heating requirements and water flow rates for terminal reheat coils and perimeter heating units throughout the building. The rest of worksheets with gray tabs provide the interim calculations placed in the computation progress. For example, the window worksheet can be used to learn the window simulation process and to review any cooling load profile related to a selected space. To select a space, simply enter the space ID in this window. The module will immediately generate the load profiles for each window of the selected space. The interim calculation worksheets are extremely efficient for learning and troubleshooting purposes. The key benefits of the module design loads are tabular format of user interface, drop-down menus, and other standard features of Microsoft Excel make the work simple, error-free and allow for linkage of the module with other spreadsheets. The open-source calculations and detailed reports are convenient for inspection, visual quality control, and learning of HVAC design methods. The module available in both inch-pound and metric units can be used all over the world.